All right. Okay. So we have one idea left from the previous set of notes to finish up. If I can find the previous set of notes here, 4-4. I have a couple of ideas left to finish. For this section, I want to talk about what it means for a function to be continuous. And I also want to talk about what it means to be an open set, which I think was some of the first definition, the first problems in the 2.2 homework ask you to identify if a set is open or not. And the reason that we care about open sets, open set. So it turns out to be the case that if you go back and look at your calculus book, most of the theorems that you prove in calculus are true for functions that are defined on open domains. As soon as you start taking derivatives, because derivatives involve limits, even a function being continuous involves a limit, right? To be continuous, a function needs to have a limit from both sides. We're going to talk about that today. In calculus 1, when you set these conditions up, they're always true on intervals that look like this. Open intervals, right? A function is differentiable on an open interval. A function is continuous on an open interval because two-sided limits can take place inside an open interval. So maybe you've never even wondered what it means when we say open interval from calculus 1. So from the standpoint of mathematics, what we mean is that any point that I choose inside that set, I can find a little interval around it that is completely contained inside the interval. So if you pick any other point inside this, pick some point inside AB, so that's a point C, you can always find some little window around it, right? A little open interval around it that's also contained inside of AB. So the fact that any point inside has this little window, that's what it means to be an open set in R. Okay? And the same rule applies in two variables or even in n variables. In the two variable case, if you have some set, let's not do a stupid set. Let's actually do one here. So here, let's do the set of all points that have the property, all points x and y, with the property that x squared plus y squared is less than 1. Less than or equal to 1. So what is that? Yeah, let's not do that. That's a half circle. Yeah, the magnitude of the vector xy is less than 1. So if I put a less than or equal to here, what I've drawn is every vector that has magnitude 1, right? This is the set of vectors of magnitude 1 in R2. So is that set an open set? If I draw it with a less than or equal to? And the answer is, well, if you go on the inside of this, can I find a little circle, a little fuzzy bordered circle contained around any point on the inside that stays completely in this set? And the answer is, yeah. I mean, at that point I can do like this little fuzzy circle around there, right? This little fuzzy circle in more technical language is called a neighborhood. That's an idea that will come up in future analysis classes for the mathematicians in here. Okay, so the neighborhood of a point is an open circle around that point, an open ball around the point. Now, is this set open? Well, no, because if I pick a point on the boundary, any open circle that I put around it will have part of it sticking out of the set and part of it in the set. But the fact that I've got this sticking on the outside means it can't be, this can't be an open set because I found a point that doesn't have a neighborhood completely contained inside the set. So to be open means every point in the set can be surrounded with a neighborhood that stays completely inside. Yep.
Is the neighborhood a circle because that is already?
It's defined to be, when you define neighborhoods, you define them to be circles, right? So I'm trying to stay away from the technical, the technical analysis, but we just define it that way because this is the natural way of thinking about what an interval looks like. So if we take an interval, we think of a center and a radius out to the edges. So if I got a 2 dimensions, I think of a center and a radius out to the edges, which gets me a circle. In 3 dimensions, a neighborhood is a little sphere with the interior as well, and then so on, right? Okay, so the basic rule is if it has hard edges, it can't be open. Here's a piece of logic for you. If a set is not open, so this set is not open, is it closed? So we also use the word closed in mathematics. And closed means something different. Closed means if you can approach it with a sequence in the set, then it is in the set, right? So this is in high level language, it's called every limit point of a set is in the set. But a closed set means that if you have a sequence of points on the inside and it approaches some number, that number that it approaches is also in the set. This is closed because it has a hard boundary. Are open and closed opposites? So this set, what is that called? Don't say donut. So what is shaped like this, where I've got like a disc with a hole cut out of it? A lot of math majors and other people that have studied this stuff in here. What is that called? It's got a special name. It's not a disc. Not a washer. Annulus was the word I was looking for. Okay, so I want you to imagine here that what I've written is the magnitude of x is less than or equal to 2, but strictly larger than 1. Is it open or closed or neither?
Open. Wait.
It's neither, right? The reason is these points out here, if you try to draw a neighborhood around them, no matter how small you make it, they're going to stick out of the set, right? So you've got these boundary points that are in the set. You can't have boundary points to be an open set. On the other hand, is every boundary point in the set? Well, no, those aren't. So these are a boundary of this set that they look like the edge of the set, but you can't actually reach them because they're not part of it, right? So this is not open because of these points, and it's also not closed because of these points in here, right? Now, why go through the trouble of introducing these ideas? It's going to turn out to be the case that the theorems involving derivatives, and there's going to be a lot of them, pretty much always specify open domains. We're talking about limits, right? And the idea with a limit is I can draw a little ball around an input and shrink it, and that makes the output shrink too. If I can't have a ball around an input, a whole ball around an input, then these theorems don't make any sense. And so when we talk about open domains, what we mean is any point you pick, you can actually pick a little ball of inputs around it that are all legal to plug in. Okay. So another way, sort of like high level way of thinking about it is an open domain is one where points near any domain element are also in the domain. You're not going to suddenly leave the domain out the edge or something. Okay. Yep.
So did we classify the circle one as closed then?
This is a closed set. Yeah.
Yeah.
This is absolutely closed. Yeah. So this is closed. This is not open or closed.
Okay, and then so it's open because if you did have a point on the boundary, you can still draw a circle around it. Is that what you're trying to say?
What do you mean?
With the inner loop? Like we're
Yeah.
saying-
So if we had if this was true, it would be an open set because no matter how close I got, I could always find some distance that I could squeeze a little ball in around,
Oh,
right?
you never even get there.
Because you never get there, right? The problem is on a set you actually include, you can actually choose that point, and then there's no way to draw the circle. Okay. So it's not something that's going to show up much, but the word open is going to appear in the definitions of these things. And it's important to keep in mind that derivatives, when we say derivatives are a local condition, what we mean is that we have to be working on the interior of some set, right? Derivatives work on the inside of sets, not on the edges. All right. Now, open and closed will show up for the math majors in topology classes and in analysis, like 412. If you take that, you'll eventually end up seeing formal definitions of open and closed. For us, I want you to think of an open set as being sort of like an interval, built out of little open spheres. Okay, so what did we leave off with last time? We defined. So last time we talked about limits. Last time we talked about limits. And so the thing that we did not get to was the idea of, well, we're trying to build up to nice functions that we can do calculus with. And so that means we're going to need to know, the nice functions of calculus begin with the continuous functions. The definition. Vectorized version of continuity. Let F take a domain. Sorry. Nothing special about the X except to distinguish it from lowercase x's. Okay. So F here is a vector valued function. It takes an n-dimensional input, it spits an m-dimensional output out. The point of this definition is it doesn't matter. It doesn't matter if it's a vector or not. The definition of continuity is the same. Let A be a vector in Rn. And we say F is continuous at A if the same condition all of you guys should at least have as a latent memory from calculus 1. F is continuous at A if the limit as x goes to A of f of x is equal to f of a. If the function gets to where it looks like it's going, the function is continuous. If f is continuous at all A in its domain, then we just say f is continuous. So continuity is a local condition. I check it point by point. And if I say a function is continuous, I mean it's that limit is equal to its value everywhere in the domain. And we have this really nice family of functions that are continuous everywhere. Except we're going to have to level up our notation a little bit because we're going to be dealing with polynomials in several variables. And that means we're going to come up with a notation for that that's convenient. So for example, something like x squared plus xy plus 2y squared plus 3xy to the third, that's a polynomial. This is polynomial x and y, or we might say a polynomial in two variables. And this can continue. I could have a 3-variable polynomial. Or if you're working on contemporary machine learning, you might have a polynomial that has 100,000 variables running around inside of it, right? Polynomials with millions of terms and hundreds of thousands of variables all mixed together. So we need some way of writing this down as an abstract object. And so we're going to use this sort of fancy looking notation. So when math professors talk about mathematical maturity, mostly what they're talking about is, do you get used to the idea that I write some sort of insane notation down and you can read it? So here is what a polynomial looks like in this context. A polynomial in n variables is a function of the form Okay. Ooh. Okay, so I have to choose a power that I can reach, right? A polynomial has a maximum power, call its degree, right? So maybe I write k is equal to k1 goes from 1 to d, and k2 goes from 1 to d, and k3 goes from 1. Now, why are all these k's? Because each variable can appear with powers ranging from 0 to d, which is going to be the maximum power that I've chosen. So d is going to represent a maximum power. I promise I'm going to explain this notation. It's going to look insane. Okay, it's going to look crazy. So I'm letting all powers of x1 go from 0 to 1 or 0 to d, and all powers of x2 go from 0 to d, and all powers of x3 go from 0 to d, all the way down until I have the sum from k n is equal to 0 to d. And now I'm going to have some coefficients, but the coefficients are indexed by k1, k2, k3, k4, k5, k6, and so on. So there's a c, but c doesn't have one subscript, it has a whole lot of them. K1, K2, K3, K4, dot, 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 out to Kn. That's the coefficient that goes with x1 to the K1, x2 to the K2, x3 to the K3, out to xn to the Kn. Look at that doozy. That's a polynomial in a vector x. Now that is a gnarly notation. What does it actually mean? So what we're saying here is that, so the more typical way of writing this is like this. So normally you just drop all of the sums into one sum, and you write ck1 up to km, x1 to the k1 out to xn to the kn. This is sort of the shorthand notation for the same idea. Okay. Now, why do we need this? Why do we need this? And the answer is, it's possible. I mean, think about the number of terms that are possible. Just if you wrote down a general polynomial, think about the general polynomial. Well, in one variable, it's easy, right? So let's say a general polynomial of degree 2 of highest power 2 in one variable. That's easy, right? C naught plus C1x plus C2x squared. That's the only one, right? That's every polynomial of degree 2. How about in two variables? Well, there's going to be a constant term where both x and y are both to the 0 power. Then there'll be a coefficient that's attached to x being to the first power and y being to the nothing. Then there'll be a coefficient where x is to the 0 power and y is to the first. Then there's going to be a coefficient where both x and y are raised to the first power. Then there'll be a coefficient where x is to the first and y is to the second. And there's a coefficient where y is to, or x is to the second and y is to the first. And there's a coefficient where x is to the second and y is also to the second. So a polynomial, a general polynomial in two variables has a lot of terms. Now I could, if you really want me to, I could write down the general polynomial in 3 variables as well. It's going to take a while. It's like 27 terms on that bad boy, I think. Yep.
On that sum at the bottom, is it km or is it also km?
It's all this is supposed to be kn. And so instead of having to do this every time, normally we just use the shorthand. It looks like this. So I don't have to come up with some way of tracking all these coefficients. I just say, pick the powers and I'll tell you the coefficient that goes with that particular power. Okay. All right, so I don't want anybody to be overwhelmed with this notation. It's useful to have this notation under our belts because a lot of the theorems that we're going to prove about derivatives actually work in n variables, not just 2. Okay. If you want the cut down version of this formula that works for 2 variable functions, you just write this. So in 2 variables, you just write the sum of Cij x to the I, y to the j. That'll work. I and j run from 0. Does that make sense? I mean, the notation is worse than the idea. Here's a theorem. One of the most useful theorems in all of analysis. Polynomials are continuous. Now, are we going to prove that? Poly proves it, and you're welcome to. The idea here is that you can always choose, because you have a maximum degree on any polynomial, you can always find like an epsilon delta argument that just using the fact that polynomials have maximum degree. Basically, we both know. But by saying polynomials continuous, what I mean is for any p of x, the limit as x goes to a of p of x is equal to p of a. What is the domain? Yep.
We also show that polynomials are continuous with infinite properties.
If you know about sequential continuity, yeah. You have to know that, like, you can't go, yeah, you can do that. Sure. But you have, yeah, but then you have to prove that the limit, you have to work with limits of polynomials in that case, right? So you have to prove it from nomials, and then, yeah, I don't know. It's kind of tricky actually to build this up. Okay. Okay, so what that means is polynomials are the natural sort of objects that, like, okay, now this is, I'm gonna be a cynic for a second here. Why do we do the things we do in math, engineering, and science? Like if you're sitting around and somebody says, oh, look at this rational function that models my physical problem. Why do you do that? Why do we insist on models that involve rational functions or polynomials? Is it because they're awesome and they're the best fitting thing that exists in the entire world? No, it's because I can actually calculate with them, right? We only use them because they work. They might be inaccurate, but they work, right? So we use them. And why do we use them? Because if I wrote down some general function and asked you to compute a limit, you would be crazy. You tell me I was crazy. I have no idea how to write. Most functions are discontinuous everywhere. And you know, I mean, that's almost every function that's ever existed and ever will exist is discontinuous at every single point in its domain. But if you have a continuous function, you can do that to it. And that means that things that are made out of polynomials are awesome too. So why rational functions? Man, you spent a lot of time in your life studying rational functions. A lot of time in your life studying rational functions. Well, why? Because a rational function is just a polynomial divided by another one. So when we do stuff like in the homework where we write f of x and y is equal to x squared minus y squared over x squared plus y squared, why choose these examples when I ask you, I don't know, could you compute the limit as x goes to, I don't know, maybe 1, of, that's a bad limit, how about 1, 2 of f of x and y, and you sort of like, just go, oh, well, I know how to do this. I just plug numbers in, right? I mean, this is 1 squared minus 2 squared over 1 squared plus 2 squared. So the limit here is minus 3 over 5. The reason you can get away with that is because these are polynomials and they're continuous. And quotients of continuous functions remain continuous. Okay. So polynomials are sweet. That's not a theorem, but you can say that anyway. Polynomials are sweet. Okay. Is that what I want to say about continuity? Continuous functions. There's a bunch of properties of continuity. I did want to point something out about an example that came up in the homework related to the way polynomials work and the relationship between limits and the values of functions. So the last thing I want to say about this is you guys were asked to evaluate something that probably most of you did automatically without thinking about what it was that you were doing. Calculate the limit as x goes to 0, 0 of the function x to the 4th minus y to the 4th over x squared plus y squared. I'm guessing that people who did that question in the homework, is this an upcoming question? Maybe it's an upcoming one. Is this upcoming? Okay. So that's an upcoming question. Now, what do you want to do with that? Is it upcoming?
Uh-huh.
All right, I'm going to answer it anyway. Okay. So because there's an important point to be illustrated here. You're going to compute that limit. Why should you even believe you can? I mean, I showed you all those terrible examples yesterday of like you take a function and you divide by 0 and all hell breaks loose, right? And that sure looks like I'm dividing by 0. So what are you going to do here? You can't just, this one you say, oh, I'll just plug in the numbers, but you know, like most math books do, they don't let you do that. They give you an example where it doesn't work. So now what? Okay, so you factor this. Now, you made this dubious assertion when you do this. This is not dubious yet, but it will be. Okay, you haven't done anything dubious yet. Haven't done anything dubious yet. That's true. Now what are you going to do? All right, so you're going to divide. Now, you got to be really careful because when you divide by something that might potentially be 0, you're cheating. That's illegal. Bridges fall down when you divide by 0. So, or that, or you know, your math professor just marks you down on your homework assignment. So, why am I allowed to do that?
Continuous function with a continuous function.
But I'm this 0, 0 still in this. Like, how do you know that I'm not at 0, 0? How do you know? You want to cancel that? I know every neuron in your brain that has been trained by 12 years of mathematics is telling you just do this. And maybe you did it without even thinking about it. You just wrote down, oh, well, obviously this is equal to this. Why is that a legal move?
You never actually get to 0.
You never get there when you're taking a limit. Now, if you wrote down, now let me tell you what would, you know, you want to get a meteor dropped on you. Off to the side, if you ever made the assertion that x squared minus y squared, x squared plus y squared is equal to x squared minus y, oh my, that's not true. Can't do that. That's illegal. Those aren't equal as functions. You just threw away, wait, certainly that would be illegal, but I meant this one. There we go. This is not equal to this as a function. As functions, that's not true, right? Because you've just divided by 0 without telling me anything in the domain. You've just potentially divided by 0. Why do your math professors insist on you putting limits on the arguments you're making? Because with a limit, it's a true statement. And without a limit, you just lied to me. Functions aren't the same. Okay? You got to be careful with this domain stuff. So, but now at this point, you say, oh, it's just, this is a 0 squared minus 0 squared, which is 0. Okay. So at the very end here, you've used one of the most deepest ideas in all of math, which is polynomials are continuous, and you didn't even give it the respect it deserved when you plug 0, and you just plug in 0. But the fact that this works, that we can evaluate limits in the way that we want to, and the justification for calculus in several variables is these properties still work. Continuity still has the feature that if I'm calculating a limit in several variables, I can still just plug numbers into it. But you should recognize, because this is a 300 level class, right? You should recognize that when we do this, we're not blindly following a rule that somebody told me back in 141, that this works precisely because we're evaluating a polynomial at some number in its domain, right? And polynomials you can plug anything into because their domains are anything, okay? This step, this only works because polynomials are continuous. Now, somebody asked me the question, well, what would you do if there was a plus up here? And my answer would be, I would draw a picture and hope. Okay. Okay. So, man, we're doing really well. We're building up this library of awesome functions that we can do calculus with, because the whole point of all of this is to be able to do calculus. So clearly, continuous functions are the nicest functions, right? I mean, they're the nicest possible functions in the world. No function could be nicer than a continuous function. So I'm going to, as an aside here, I'm going to point out that continuous functions, I just said polynomials are sweet, right? But continuous functions are not. So continuous functions aren't good enough. There's things that we want to eliminate. We want to study surfaces and we want to study physical behavior. But the problem with continuous functions is I can write awful continuous functions. For example, that's continuous. If I want to study the behavior of a system determined by this function, and I say, oh, what's the rate of change of the system? You're totally okay over here. And then you go over here and you're totally okay. But then there's this point right here where, well, there's not a smooth change in the behavior of the system. There's this edge, right? So if I was trying to look at a function like this and describe how the shape was changing, I can't. It's not defined there how the shape is changing. In fact, actually the worst sort of, you guys ever seen a cusp before? You know what a cusp is? So a cusp is even worse than one of these because at least this has a derivative from this side and a derivative from that side. At a cusp, you get behavior that looks like, oh man, this. Ew. Now, not only is the function not have a well-defined way of talking about how it's growing at that point, it's vertical. Well, it's continuous. I mean, it's still, you can draw without lifting your pen, so it's a continuous function, right? The limit is still 0 at 0 here. This is continuous. I don't want to study physical systems with things that look like this. Back in the 1700s, this dude called Weierstrass cooked up an example of a function that's so bad that it made other mathematicians accuse him of working with the devil. The idea is you take a function, just imagine you take a sine function like that, right? And then you cut the sine function in half and you put a sine function on top of it. And then you cut those in half and you put sine functions on top of those, right? So now that's the first step would be to take that sine function and cut it up into 2 sine functions. Then on top of that one, take each of those 2 sine functions and make it into 2 more sine functions. And so you get a little wiggly dude that looks like that. If you keep that process going, you end up with a function that kind of looks like this. So that function is continuous and nowhere differentiable. There's no derivative. It looks like an infinite stack of, remember that sine over 1 over x I showed you last time? It looks like sine of 1 over x at every single point in the domain. So it's just this static fuzz of sine functions just blasting away vertically. This is continuous. Ugh. So the goal of all of this is to build calculus, but I'm going to need more than a function being continuous to make that true. And so that's where the idea of derivatives comes in. Derivatives you should think of as not just being a way of computing a slope, but of asserting behavior of a function. If a function is differentiable, so I want you to think in the reverse way as we go and talk about derivatives. We're going to talk about derivatives now. These are all examples of terrible continuous functions. If a function is differentiable, it can't do this. It can't. The slopes have to match for a function to be differentiable. So differentiable functions aren't just functions you can study with tangent lines. Differentiable functions are smooth, right? They're well behaved. They don't do this, and they don't do this, and they don't do that. Differentiable functions are nicer than continuous functions. So what is the upshot of all that? It is harder differentiable than continuous. Even in one variable, right? Even in one variable. And in 2 variables, things are going to get way worse. So when we find a function that's continuous, that's differentiable in 2 variables, we're going to be really happy. And in fact, like good applied mathematicians or engineers, we're basically going to restrict our attention to good functions. We're going to identify what the good condition is, and we're going to say we're only going to work with those. Okay, so I have a tiny quiz for you. I'm not making you do it on paper, but if I walked around the room right now and put this chalk on somebody's desk, and I said, write down the definition of what it means for a function to be like differentiable at a point A. The 141 definition. If I said right now, Write down for me the definition of what it means to say f is a real valued function on the real numbers and it's differentiable at a point A in its domain. F from R to R. I'll give you the first half of the theorem. It's just for free. F from R to R is differentiable at A if there's a big empty space on the board right here. You didn't think you could forget everything you learned in passing in 2 days of lecture 3 years ago. What does it mean to be differentiable at A? Yep.
If a particular
And that limit is?
would be f of x.
Okay.
Hold on. I'm going to tell you the bottom of that.
Oh, okay.
Okay, I'm going to do it all out of order, so it'll be very fun.
Okay.
Okay, limit x goes to a.
Oh, that definition. Okay.
Yeah, we're gonna.
Okay.
Yeah,
Either one is worth money. I
This
mean,
one
not
is-
I mean
this one
abstract
is-
money.
this
Abstract
one
money.
is better. This is better. X and then in the numerator. F
Okay.
minus fa
Yeah.
all over x minus a.
Okay.
If that exists.
Yeah. Okay. If this limit exists. Sweet. Now, somebody else tell me the other definition.
The limit as h goes to 0
Awesome.
of f of x,
Well,
sorry, f of h.
so remember, we're working at a point A here, so you don't have to do it for a general X. I'll tell you that what you want here is A.
Okay, yeah, f of a minus or plus h. So minus f of h. F of a, sorry. Jeez. All divided by h.
All right. Sweet. Now, we're going to be using these difference quotients to like determine what it means to be a derivative. And we have to pick one of them, which is more ideal for working in several variables. And even though these definitions are equivalent in one variable, one of them is more useful than the other one. Okay. What I do want you to, I'm not going to tell you which one yet. Now, congratulations for those of you that managed to cough that up out of your brains, especially the 8 or 9 of you in here who are shy and just didn't feel like taking a risk. What is a derivative? Change of something, rate of change. Okay, so, all right, so here's what we started with. What is a derivative? Okay, so one answer is a derivative is literally whatever this limit happens to be, right? Okay, but your interpretation, so far we have, what is a derivative? I've heard rate of change twice. What else is a derivative? Slope at a point. Okay, slope. So yeah, what you guys just said is the same thing basically. So slope at a point. What does that mean? Slope? Slope of what? Slope of a tangent line at a point. Okay, so slope of a tangent line. Okay, so of course, what is a tangent line?
It's lines with such a something in multiple places.
A line that
It's perpendicular to that point.
perpendicular to the point.
Where that point's going.
Where? Where that point is going. That's good. All right, where that point is going. I mean, that's actually it's a reasonable statement. So for those of you that are saying tangent line, it's basically this, right? That's what you have in mind with tangent lines. What else is it? So there's another idea here that nobody has said yet, which is the single most important idea of the first year calculus sequence. And maybe your teacher spent 15 minutes on it.
What is the derivative question?
Yeah, no, the answer to the question, what is a derivative? There's one answer that nobody has said yet that is the most important reason the derivative exists. Not okay, that is super important, but we're talking about the derivative we're not talking about the fundamental theorem of calculus or abstract derivatives right now. We're talking about the derivative as a number. Okay, also good. Inverse of integration, perfect. Still not the most, you spend tons of time in Calculus 1 talking about that, right? What else is it? What sort of object is a tangent line? Is it a curve? It's a line, right? A tangent line is a line. What good is it? What good is a tangent line? I'm going to remind you that every single time you learned about a new way to take a derivative in Calculus 1, the very first thing you did with it was compute a tangent line. It was like clockwork. You knew. Oh, we learned how to take a product, a derivative of products. Well, I got to have to compute more damn tangent lines, right? They do identify critical points when slope is equal to 0, right? Okay, still not what I'm after.
Is it finding the slope of the curve?
Okay, that's still not what I'm after.
Approximation.
Ah, there we go, finally. Okay, derivatives give you approximations of curves, right? So the secret of calculus, you guys, this is a great pile of answers you guys gave me, by the way. This is like, you pretty much mined out everything a derivative in one variable is, right? So the secret of calculus, so you're the Wizard of Oz, you're in the Wizard of Oz, and you look behind the curtain. What is the secret of calculus? The secret of calculus is everything is actually just a line. And that's what you did, right? You spent a year learning math where all you did all the time was reduce things to lines, right? Every single function you ever worked with was one you could just say, oh, well, I don't care about the function. I'm going to replace it with its tangent line, right? Every working mathematician, every working engineer that works in linear approximation, which is basically everybody, says, man, I got this differential equation. I have this physical system that I'm studying, and the answer is awful, right? I got this super squiggly curve coming out here, and I don't know how to predict what that value, I know that value right there, and I sure would love to predict what happens right there. What do? You pretend it's a line, and you say, oh, I don't know what the curve does, but I'm going to draw a line, and wherever the line goes, that's what I'm going to say what the function does. The whole point of differential calculus, for all that we give it basically none of the time that it deserves, the whole point of differential calculus is that f of x is about equal to f of a plus f prime of a times x minus a. This is the entire point of the entire quarter of calculus, is that statement holds. What is the derivative? It's the slope you put right there. When is a function differentiable? When this is a good approximation. And yeah, if you go back and actually look at your Calculus 1 curriculum, you're going to see that showed up for seriously 15 minutes in the one section on linear approximation where they made you estimate the sum of the square root of 4.01 or something like that. Right? But the point of a derivative, the whole point of a derivative is that I can take a function and replace it at a point with a line. I don't ever have to work with hard formulas. I can always work with tangent lines instead. So the whole point of a derivative is that functions are approximated by lines. The entire point of the subject is that functions can be replaced with linear approximations. Okay? And so the machinery that we're going to build about derivatives had better be able to recover the fact that we want to approximate our multivariable graphs with something that looks like a line. Of course, there's going to be a problem. If I have a paraboloid, say I'm working in 2 dimensions and I've got some paraboloid, and so here we go. Here's my paraboloid. Let's just say I pick a point on that on the surface right there, and I want to approximate this paraboloid, which is it's sitting in 3 dimensions, right? I want to approximate this thing with something. I mean, something flat, I guess, because I approximated this curve with a line, but there's a lot of lines that approximate this thing, right? I mean, if I drew through it like this, I imagine I draw through the parabola with a circle, and I took the tangent line to the circle, I'm going to get some line that sort of sticks out of the parabola looking like that, that's tangent to it at that point, yeah? Like that, you can think about like this is a curved surface and the tangent sort of sticking out of it, approximating the curve of the parabola, yeah? But what if you drew a different line? Well, there's going to be a different vector that approximates the surface. And if you took a different curve through the point, there'll be a different vector that's a tangent line to that curve. Every three-dimensional curve that you draw, if you calculate its tangent line, it's gonna just kiss the parabola in the sort of tangent line way. So what are we going to approximate this with? A plane turns out to be the answer in 2 dimensions, right? And what we want to say is, instead of having here, this is actually easier to imagine if you imagine this sort of a sphere instead, right? The idea is that if you pick the point on the sphere, what you want to do is you want to say, okay, I don't care. I mean, one line isn't going to be good enough. A sphere locally looks flat, like a plane, right? And as I move around the sphere, the orientation of the plane is going to shift to match the sphere. So there's still a notion of direction. And there's still a notion that if you were close enough to the top of the sphere, or if you were close enough to the original point, I mean, then the plane actually does a pretty good job of approximating where you were. If you want to know where this point right here is, you could just say, oh, we'll go out there on the plane instead. That point and that point are close approximations of each other. I can replace this complicated surface with a plane, which is easy to work with. So what we're trying to do is build a notion of derivative that lets us do this move right here. So the goal is not tangent. The goal is to come up with something that looks like this. I want to be able to come up with an idea of derivatives that lets me do linear approximation. But instead of working with lines, I'm going to be working with planes instead. Okay. So this is kind of what the definition of what we're doing has to do. And when functions have this good approximation property, those are the ones that we're going to call differentiable. Just like over here, functions that were differentiable had good tangent lines. Surfaces that are differentiable will have good tangent planes. Okay. Now, the reason I'm not delving into more specifics here and I'm being really vague is because I don't want to pile a bunch of technical stuff on you 3 minutes before the end of class, or I would have actually like begun doing some of this stuff. So next time, what we're going to do is so let me give you a plan of where we're going. You might want to read ahead if you haven't seen this stuff in a while. But I have been told by several people, I think I mentioned this stuff to you guys before, that hardly anybody in here, I did not say this, this is somebody else saying, that many students in here will be uncomfortable with the idea of a partial derivative. Like if I just said, calculate some crazy partial derivative, that a lot of people haven't seen it in a long time, right? So we're going to start with the definition of partial derivatives. We're going to build up the idea of using partial derivatives to find these tangent planes. So partial derivatives are going to give us a method we can use for figuring out when these functions have tangent planes and what their definitions are. So partial derivatives lead to tangent planes in the same way that classical derivatives lead to tangent lines. That's why we do them. All right, so I'll see you guys tomorrow. Sure.
So I missed the last 2 weeks Wednesday class.
Yep.
Like up to here.
Oh man, just come in the office hour. Chat with me. Yeah.
And the last Wednesday, have you touched on anything, any of like this or like further?
I did. So yeah. So that was stuff I did in examples. So it's not. It's gonna be. Send me a message or something. I'll show you how to do it. It really. It's not complicated.
Okay. I'll go back watch Wednesday and then get in touch with you.